So our next speaker is David Monniaux, and he's been extending CompCert with optimizations and the introduction of security features. So he's going to tell us about this as soon as he gets the right desktop. There we go.
Wonderful. So yes, I'm going to talk about memory simulations and how we use them to implement security and optimization features in CompCert. So let's see. First, I give a short introduction to CompCert. I assume that in this community, everybody knows about it, but it's not necessarily the case for everybody. So it's a formally verified compiler for the C programming language, or at least a very large subset of the C standard. And it is an effort led by Xavier Leroy, who is not here, and Sandrine, who is here. And there's a theorem that says that if compilation succeeds, then the assembly program matches the C program. And when I say formally verified, this means that the compiler is mostly written in the cock-proof assistant, and there's a correctness theorem also proved in the cock-proof assistant. And what is the rationale for that? In certain industries, it started with the avionics industry, you must demonstrate that your object code is sort of equivalent to the source code, so that you don't have any gap in the overall safety argument for your system. And the conventional approach, and I recall talking with Airbus about that, was that they would disable, use a normal compiler and would essentially disable most of the optimizations so that the assembly code would look sufficiently like the C source code, and they would be convinced that the compiler was not trying to be too clever. And of course, this is not very satisfactory because you get a very inefficient code as the outcome. So essentially in CompCert, you can replace this argument by the mathematical proof, and you can turn optimizations on. So that's the rationale of that. So I'm going to discuss in this talk two versions. So there's the one that you can download from GitHub and from the company that markets the commercial version of CompCert, called Absinthe. So it's on the GitHub site. And our own branch, which is on our own GitLab site, which is called Chamois, because we're doing agile development, and Chamois is a very agile animal living in the mountains near Grenoble. And so let's look at this correctness theorem. The correctness theorem says that if you have a formal semantics of C or something sufficiently close to C, and your program, when you run it, it emits a sequence of externally visible events. Okay? It has its internal affairs, and it has things that interact with the external world. And the external world is things like a call to external functions, such as system calls, or accesses to volatile variables, especially you would think of volatile variables that map to system registers and actually act on the hardware. I mean, if you're thinking low-level code, things that people put in safety-critical embedded systems, then they certainly have to interact with the hardware of that system. And you want that the trace at the assembly level matches the trace at the C level, assuming, of course, that your C program does not encounter undefined behavior. Of course, if you do undefined behavior, then you have no guarantee what happens at the assembly level. And this proof is obtained, it's a bit complicated, but it boils down to some format simulation proofs of each of the internal passes of the compiler. So you prove that the program, after executing one transformation pass, simulates the program before the transformation pass. And the relationship between the state of the program before the transformation pass and the state of the program after the transformation pass is expressed through a match relation between states. In the simplest case, your simulation proof is lockstep, meaning that you have one step in the program before the transformation, and this one step is matched by one step of the program after the transformation. So this happens, for instance, in phases where you just, for instance, some kind of common sub-expression elimination, you recognize that you already have a value that you would like to compute, and instead of computing it, you just copy the register. So that would be lockstep. A plus simulation, you have one step in the original program, then you map to several steps in the target program, and for instance, function call. At some intermediate representation, function call is just one instruction, and in reality, you know that you have to take several steps to put the arguments into the right registers and save stuff and so on. And in the most general case, you have to you replace all sequences of instruction by other sequences of instructions. And now this match relationship, and this is really the hard part when you are trying to prove the correctness of some transformation paths. You are at the level where we are when we did most of our work in CompCert. Your current state of execution of the program consists of the program counter, which is local to the function that is currently under execution, an abstract view of the stack. So you have a bunch of stack frames that record the caller functions in the order in which they call them each other. And these abstract stack frames, they recall in which function you were and which program counter you were. You have values. You have an unbounded number of pseudo registers, and you have values in these pseudo registers, and you have values in addressable memory. One important point is that you may have undefined values. It's the vundef value, if you know the CompCert source code. And this undefined value may be refined by a transformation pass on the program. So if you have a program that generates somehow an undefined value, then the compiler is allowed to replace this undefined value by something else. For instance, if you add an operation like division by 0 that you would define to yield an undefined value when you divide by 0, you would be allowed to replace that by, I don't know, 0 or 1, because on your favorite processor, the division instruction outputs 0 or 1 or whatever in the register as the result of the division. If your divisor is 0, you would be allowed to do that. You are also allowed, if you encounter undefined behavior, if your program gets stuck, and this is undefined behavior that essentially means if you get stuck, that would trap the program, the compiler is allowed to transform that into a program that still continues executing. So for instance, if you have a program that does a division by 0 at the C level, this is undefined behavior. But you're allowed to replace that by an instruction that continues execution with maybe some undefined value in the result register. That is legal. And so in most, I'm mentioning this about definedness because in most matched relations, you have a notion that the state after the transformation is more defined somehow than the state before the transformation. And now the delicate part in most cases is dealing with memory. Values in pseudo registers in general, the proofs are not too complicated, but the memory part is the complicated part. So CompCert's memory model is that memory is divided into blocks. And they sort of model if you read the C standard, they talk about memory objects, and these blocks model the memory objects in the C standard. And an address consists of a pair between the identifier of the block and some offset within the block. And the idea is that you're not allowed to freely move between blocks. You are not allowed to do pointer arithmetic that would jump from a block to another block, okay? This is actually prohibited by the C standard anyway. And the operations is that you can allocate a block, free a block, read from an address, write to an address, and you're also allowed to decrease permission. You can turn the data read-only, for instance. And you have, if you want, you're trying to do proofs on this optimization or transformation passes, you have two very important notions with respect to memory. You have the notion of memory extension. So memory extension means that a state of memory extends another one. If you keep the same block numbers, but the blocks in the transform memory are longer. They have more bytes. They have more space. They have more space at the end. So, for instance, you may extend your stack frames. If you do a transformation pass that, for instance, needs to spill some values into the stack frame, then you can say, well, the stack frame after this pass is longer than the stack frame before this pass, and you stuff extra values at the end. If you some other passes need some more complicated notion of matches between memory. It's called memory injection. It means that each block before the injection maps to a sub-block after the injection, or may actually map to nowhere. It's more complicated, but it enables you, for instance, to, when you do function inlining, you have to you're not only inlining the code of the inline function into your caller function, you also have to stick the two stack frame together and to get a bigger stack frame. So this means that you're mapping the blocks before that would correspond to these stack frames before the transformation into one single block. I mentioned external calls. So what can external calls do in your memory? The axiomatization in CompCert is essentially then they can change things in memory almost completely freely. So this means that you do a call to a library function. It's allowed to change anything, and your optimizations cannot assume that memory is left untouched, except that if before your program transformation your external call succeeded, then after your program transformation, the external call should succeed even if you apply. Should succeed and give the same outcome, even if you applied a memory extension or a memory injection. So you have axioms that say that external call commute with the memory extensions and injections. So this was preliminary. Now the things that are in the paper. We were interested in developing things, countermeasures against attacks. So this is the beginning of our work on a countermeasure against attack. And so the chamois is a rather shy animal. So we call that bouquetin because that's an animal with big horns, which also lives in the mountains near Grenoble. And it can defend itself, sort of. So we did stack canaries. So it's the protection against buffer overflow attacks. So if you're not familiar with buffer overflow attacks, imagine that you allocate a buffer on the stack. You're in C. Nobody checks that your accesses are within bounds. Okay? This is undefined behavior if you access out of the bounds. Of course, at some point you will write code that doesn't properly check your bounds. For instance, you're decompressing some file that somebody sent you by email, and your code is correct if the file is correct, but the file has been intentionally corrupted, and then when you decompress, you get out of the buffer, and after the buffer, there is the return address of your function. Maybe you can cleverly design a file that would put a certain value into this return address, and then you return from the function at an arbitrary location, maybe inside the file that you've just downloaded, and then you execute arbitrary code. So this is the simple version of the buffer overflow attack, at least the version that was popular around 1996. Of course, nowadays, you cannot just do that easily on a processor, on something that runs on your laptop, okay? There are many countermeasures that are implemented at the level of the operating system and the compiler and so on. Nowadays, you still have variants on this buffer overflow attack, but they're much more complicated because they have to work around the countermeasures that are at the level of the operating system. So you cannot easily predict addresses to which you have to jump. The stack is not executable, so you cannot just jump into code locations in the stack. Data is normally not executable, and so on, and so on. Okay. But you may notice that many of these countermeasures assume that you're running on something with a full operating system that can randomize addresses and then can have execution protection against certain locations in memory, typically something that runs on a processor that has a memory management unit. If you're running on an embedded system, you may not have a memory management unit. Your code may be at a fixed address because you have the code that runs on the system is compiled with completely static addresses. It's maybe in ROM. So it's not necessarily, all these countermeasures not necessarily work. And anyways, there are ways to work around them. So there is another simple, very simple countermeasures that you can insert at compile time, which is called a stack canary. So what you do is that before the return address, you put a kind of value that you get. You take a random value and start executing the program. And when you start executing a function that could be attacked, you put the value just before the return address, or at least somewhere after the local variables. And if the attacker manages to clobber the return address, typically they have to do it by clobbering continuous areas of memory. So it will clobber the canary, and if the canary contains an incorrect value when you exit the function, you kill the program. So it's called a canary because it's like the canaries that were used in coal mines to warn miners about carbon monoxide. They get killed before the miner gets killed. And so the countermeasure is rather easy to implement. You extend the allocation size. At the function prologue, you install the canary at the right location. At the function epilogue, just before a return instruction or before a tail call instruction, you check that the canary is still in position and branch the trapping instruction if not. And you have to prove correctness for that. You prove that you do not perturb normal executions of the program. So currently, I don't have a proof of adequation, which would mean that I would prove to this attack blocks a certain model of intruder, and it's because I don't have a nice idea of a model of an intruder that necessarily attacks contiguous amounts of memory without guessing a special value. It doesn't seem like a very good definition of an intruder. I will need to think about that. So this is proved by memory extension. Another interesting thing that you can prove with playing with memory relationship is a variant on tail call elimination. So there's already a tail call elimination in CompCert. It replaces, when you have a call at the tail position inside in a function, you can replace it by a kind of a jump to the head of the function that you're calling. And during a tail call, the stack frame of the current function is destroyed. You jump to the head of the other function, and it creates its stack frame. So it's what it does is it avoids, when you have maybe mutually recursive functions, it avoids creating many stack frames on the stack that use up memory that has no usefulness. So that's the interest of this optimization, and it already exists. Now, if you do that on a recursive function, the code will do is it does its recursive call by deallocating the current stack frame. So this means that you're restoring the registers that you saved. Then you jump to the head of yourself, and then you reallocate a new stack frame and you save the registers again, which seems completely silly. And you say, why am I saving things and restoring them at the same location all the time? And ideally, what you would like to do, yes, is a transformation that simply replaces tail calls into a regular loop. And you just stuff the arguments into pseudo registers, branch to the top of the function, do not save and restore. And you can actually do it. And the simulation proof is a memory injection. Essentially, you are simulating the stack frame of yourself when you call yourself recursively using your current stack frame. It's a bit tricky, but it works. So you were asking me to conclude, and I'm concluding. So the point of this talk is to illustrate how security and optimization features that deal with memory can be proved simply through memory injection and extensions. Because when we develop things inside Chamois, we want to maximize compatibility with the existing Git code base for CompCert. So if we can reuse the same framework, the same axioms about external calls, it's much better for us. Something that I did not discuss during the talk because I think I would have been over time if I had done that. No, I would. Okay. We also have pointer authentication on the Arch64 platform. You know that the Arch64 platform, like on recent Mac computers, you can authenticate pointers, and it's yet another method to thwart buffer overflow attacks and things that corrupt pointers. And we currently have a version that, like GCC does, authenticates the return address. It's a bit tricky. The way we currently do it does not commute with injections, but this is not a problem because this is applied very late in the compilation process, and we don't run phases that need memory injections after that. So we're allowed to do it in this way. Otherwise, if we wanted to have a general framework for pointer authentication, offering a way at the source level to say that certain pointers are authenticated, like the Clang does on macOS, then we would have to have a more general framework, but then it would need extensive modifications to CompCert on the value type everywhere. So we have not done that. And this is the advertisement for developments. This is also an advertisement because we are recruiting, we have faculty positions open. Contact me if you're interested.
Thank you. Do we have questions for David? Andrew?
I'm very encouraged to see your work on tail call optimizations because this is an area of interest for anyone who tries to compile functional programming languages into C, and this is an area where CompCert is noticeably weaker than GCC and Clang. So
thank you.
I think there's even more you could do there.
I had one question about the memory injections. So do you have in mind other transformations, or optimizations, or countermeasures that you could use the concept of memory injections to verify?
So currently, we're trying to implement countermeasures against hardware attacks that would, for instance, keep instructions. So we're trying to not only to prove correctness of the transformation in the presence, in the absence, sorry, of an attack, but we're also trying to prove adequacy of the countermeasure against a certain model of the attacker. Now, if you want to do that, some people would say that you have to duplicate completely the memory and do writes to memory at several locations, but I don't see how to do it without breaking many things and without breaking binary compatibility. So we'll not change the way we store things in memory in order to implement that. I'm sorry. We'll just duplicate loads and so on.
Thanks. Yes.
Hello, Loïc Puget from Stockholm University. I think nowadays GCC also implements some protection against spectre and meltdown. Do you also have plans to do that?
Okay. So there's an answer here. Is that the security work that we do is funded by some kind of big grant, and we're in a part of the grant that deals with more like embedded systems, and the Spectre kind of attacks are more like a data center or maybe a phone or something like that, more bigger processors. So in theory, we're not concerned with it. But that would be very, actually, that I find it very interesting. Now, the proving correctness for this kind of countermeasures is one thing. Proving adequacy with respect to a model of the attacker, then you have a model of the attacker that talks about the macro architecture. And that's tough, I think.
Looks like a good conclusion. That's tough. Okay. Yeah, let's thanks David again.